Namaste everyone. Welcome to second PUC physics class. We were discussing about AC circuits, series resonance circuit. Namaste, hope you are doing well. Welcome to the class. We discussed about series resonance circuit, its resonance frequency, and at what frequency the maximum current occurs, what happens at that maximum current position, that is inductive and capacitive reactances cancel each other, they become equal, and voltage across L and C cancel each other. Circuit becomes purely resistive, and the current will be in phase with the voltage. Only resistor will be in charge, right? So all the voltage appears across resistor. Of course, there is voltage across L and C also. Across inductor and capacitor there is voltage drop, but they cancel each other. You know that phasor diagram, they are exactly opposite. Only voltage across resistor will be the full voltage, and when we work out problems we will take care of that, whether we get the same situation or not, we will see that. And but still theory of this chapter is not yet over. That is we have one more thing in that, that is power dissipated in AC circuit. Already I have given the formula. I have given the formula like this. Power dissipated in any AC circuit, P is equal to Vrms into Irms into cos phi. That's what I have written. See, if you analyze this formula, P is equal to Vrms into Irms into cos phi. Okay. So this is the general formula for power dissipated in any AC circuit. If you apply it to different cases, then you will get it like this. In the case of purely resistive circuit, if it is resistive circuit, in resistive circuit, phase difference is zero. Current and voltages are in phase in the sense there is no difference in phase. When current is maximum, voltage is also maximum. When current is zero, voltage is also zero. So they attain the same values together, same instants together. So same instantaneous values together. So phi is zero. If it is zero, what is power factor? This is called power factor. Power factor, then power factor cos 0 is equal to 1 in a resistive circuit. So power dissipated is similar to in a DC circuit, Vrms into Irms. What about in purely inductive or capacitive circuit? In a purely inductive or capacitive circuit, phase difference between current and voltage is 90 degrees. Either current will be leading or voltage will be lagging. So or voltage will be leading. Then power factor cos phi is equal to cos pi by 2, that is equal to 0. So power dissipated is Vrms Irms into 0, that is equal to 0. No power is lost in AC circuit containing capacitor and inductor only in the form of heat. No power is lost in the form of heat if an AC circuit contains pure capacitor or pure inductor. If it is resistor, of course there is a dissipation of power, it is not zero. So that is why current in a purely capacitive or purely inductive circuit is called wattless current. So this is called wattless current. So maybe a definition for 1 mark, wattless current. Okay, now how did you get this equation? P is power factor. So this is called true power, this is called apparent power, P. So cos phi is power factor. Vrms into Irms, that product is the true power. Okay, now how do you get that equation? That is very simple. It is like this. Now in a series resonance circuit, at any moment, how do you write the phase difference between current and voltage at any moment? So we write it like this. It is R and this is C, okay, this is L. V is equal to Vm sin omega t is the applied voltage, alternating EMF, right? I is equal to Im sin omega t plus phi is the phase difference between the current and voltage. This is the current in the circuit. So this current may be leading or lagging because phi may not be positive always. Whether phi is positive or phi is negative depends on the value of phi, that is tan phi is equal to xc minus xl by r. In lower frequencies, again the same story. I don't know whether you get bored or not by repeating this sentence, but still it is very much needed. At very low frequencies, capacitive reactance is very high. You know, xc. I repeatedly write these formulas because that makes you perfect. Otherwise, it is not. It will not be. So you will find it very difficult to remember the formulas. 2 pi nu L. So at lower frequencies, capacitive reactance will be very high and Xc is greater than XL, and this is positive. Phi is positive means current leads, plus phi. And at very high frequencies, XL is greater, XC will be lower because nu comes in the denominator. And what happens to this? This becomes negative, phi becomes negative. That means current lags behind. At exactly the resonant frequency, what happens? XC equal to XL. XC minus XL is 0, but R is not 0. Tan phi is 0, phi is 0. So analyze it. Every result can be analyzed like this. So at resonance, phi becomes 0. Phi 0 means I is equal to Im sin omega t. What do you mean by that? V is equal to Vm sin omega t, I is equal to Im sin omega t. Both are same. Both are identical equations. That means current is in phase with the voltage and circuit becomes purely resistive. That's what happens. Now, these are the voltages and current. Now, what is the power developed? Power developed in AC is equal to V into I, instantaneous voltage into instantaneous current. V into I is equal to Vm sin omega t, that is applied voltage, Im sin omega t plus phi. This is the power developed in the form of heat. Okay, I can write it like this. Mathematically, I am going to prove it now. That this is the formula for power. P is equal to V into I, Vm Im sin omega t into sin omega t plus phi. So using trigonometric formulas, you have to solve this one. Sin omega t into sin omega t plus phi. We have a formula cos x minus cos y is equal to minus 2 sin x plus y by 2 sin x minus y by 2. Don't know whether you remember this formula or not. I too don't remember this formula, but for the time being I remember this. There are so many trigonometric formulas. For physics, it is enough if you remember certain formulas, but trigonometry is very much needed in these types of solution also, analytical solutions. Okay, minus 2 sin x plus y by 2 sin x minus y by 2, that gives cos x minus cos y. Similarly, you have sin A minus sin B, sin A minus B, so many things, right? Sin A into sin B, all the solutions. Okay, now this is very much needed here, because if you use this, what happens to this is, see, this is in this form, right? So what I will get here, if I put it like this, power is equal to Vm into Im, this becomes cos phi minus cos 2 omega t. Of course, this is only the solution of this part. I am writing the solution of this part only now. Cos phi minus cos 2 omega t plus phi. This is the solution. Vm into Im into cos phi minus cos 2 omega t plus phi. I remember it like this. This is a very simple situation, because finally this should remain, isn't it? Cos phi. That should remain, and this should go off. And because this should be the formula finally. I am teaching in a wrong way actually, but still for the sake of examination this is very much needed. Finally this should remain. So cos phi minus cos 2 omega t plus phi. Or if you apply this cos phi and this one here, if you apply this to this formula, will you get back this one? That's what you have to check, right? We will get back this cos phi minus cos 2 omega t plus phi. Whether this will give you sin omega t plus sin omega t into sin omega t plus phi. Yes. See, minus 2. I will put this now. Minus 2 cos x minus cos y, this is x, this is y, correct? Minus 2 sin x plus y by 2, x plus y by 2, phi plus 2 omega t plus phi, 2 omega t plus 2 phi by 2, correct? Minus 2 sin x plus y by 2, x is phi, y is 2 omega t plus phi. So 2 omega t plus 2 phi by 2, and then sin x minus y by 2. X minus y by 2 means phi minus 2 omega t minus 5. So phi minus 2 omega t minus 5, minus 2 omega t by 2. Am I right? And you have one minus here also. Sin of minus theta is minus sin theta, so that gets cancelled. So what you will get? You will get it as minus 2 sin. You should get finally this one, right? Minus 2 sin omega t plus t by 2 cos omega t minus 2 by 2 sin omega t into sin omega t plus t by 2. That's what you have to get. Yeah, I think then you have to get here one thing. This is Vm by 2 you have to do. That's one more thing. One more thing you have to. This answer is Vm Im by 2 into cos phi minus cos 2 omega t by 2. Okay, so if this comes to then, this comes to this much, right? Cos phi minus cos 2 omega t plus phi is minus 2 sin 2 omega t plus 2 phi by 2 sin 2 minus 2 omega t plus by 2. This 2 gets cancelled, right? This 2 gets cancelled, and here you have Vm Im by 2, and this 2 gets cancelled, and sine of minus theta is minus sine theta. That minus sign gets cancelled. So finally what will remain? Vm Im into sine omega t plus phi, sorry, omega t plus only 2 gets cancelled, phi will remain, omega t plus phi and sine omega t. Of course, sine of minus omega t is minus sine omega t, that minus gets cancelled with this one. So whether it is the same equation, right? We will get back this equation. Vm Im sine omega t plus phi sine omega t. So I'll rub that. I just proved that the equations are same. So you will get it back if you use this equation. So finally you will approach to this equation, or you will arrive at this equation. Vm Im by 2 into cos phi minus cos 2 omega t plus phi. So substitute here cos x minus cos phi equal minus 2 sin x plus y by 2 sin x minus y by 2. You will get back this equation. So this 2 will cancel with this 2, whatever is extra you put. 2 sin phi plus 2 omega t plus phi by 2 sine phi minus 2 omega t minus phi by 2. So you will get back that. This is what we will arrive. So that is this one. Now suppose you want to find out average power dissipated. We did it for a resistive circuit and capacitive circuit, you may be knowing. If you find out the average power dissipated, then what is the answer? Vm Im by 2, and here you say, here what is the average? Average of what is 0? Average of sine theta cos theta is 0, provided theta is a variable. If theta is a constant, how can it be 0, right? Cos 0, 1, always 1. If you are summing the values, average values, if you are finding the average values for whole 360 degrees, then cos theta sin theta is 0. But here it's a phi. Phi is the phase difference between current and voltage, and it doesn't move from 0 to 360. It is not summed over all the values. So phi is not a function of time, not a variable, or not a function of time. It is not a function of time. It is independent, right? It is independent of time, whereas this one is a function of time. This varies, so this average is 0. Cos 2 omega t plus phi, that average value is 0, whereas cos phi, its average value is not 0. So which will remain? So when you put the average value of power dissipated, P is equal to Vm Im by 2, Vm Im by 2 and into cos phi. That survives. This becomes 0. Okay, I think you have followed. Sin theta cos theta average value over the full cycle is 0. From 0 to 360 degree, 2 pi. If it is not varying, if it is a constant, it cannot be 0. So this survives when you take the average power for the whole cycle, one cycle of AC. This doesn't survive, it becomes 0 because it is a function of time, and you know that as the time passes, the AC completes all the cycles, right? So full AC cycle, for full cycle this is 0. So how can you write this? Of course, this is the average power is the average of this value. Average power is average of all these values. That this survives, so average of this, and that is not 0. Okay, so average power dissipated, I'll write it like this. Average power dissipated is Vm Im by 2 into cos phi, that is Vm by root 2, Im by root 2 into cos phi. So what is average power then dissipated in an AC circuit? Average power is equal to Vrms into Irms into cos phi. This is the formula, right? So I think you have followed it, right? So even in the case of resistor and capacitor we do that, right? But in the case of capacitor and inductor it becomes 0 because we get the two equations. One is sin omega t, another is sin omega t plus pi by 2, that is cos omega t. Sin omega t, cos omega t. So that leads to average power 0. Both are the functions of time. Sin omega t and cos omega t, both are the functions of time. So if I can put it in a nutshell like this, suppose it is asked, but it's not an important answer. Not an important question. You won't get a question like obtain the average power dissipated in a resistive, capacitive or inductive circuit. It may be 1 mark or 2 mark question. An equation for that is not a very important question. So in a resistive circuit, you know that current and voltages are in phase. So V is equal to Vm sin omega t is the applied voltage, then I is equal to Im sin omega t is the current. There is no phase difference between current and voltage. So power is V into I, instantaneous voltage and current, Vm Im sin square omega t, right? It is not zero average power, because you can, if you want to find out the average power dissipated, Vm Im into average of sin square omega t. Average of sin square theta is 1 minus cos 2 omega t by 2. So you can expand it. Vm Im, it is an average of 1 minus cos 2 omega t by 2. This average. But 1 minus cos 2 omega t, half minus cos 2 omega t by 2. This is a function of time, its average is 0. So what will remain? Only half. 1 minus 0 by 2. So you will write average power is Vm Im, average of this is half, which can be written as Vrms into Irms, right? So where you can prove it like this, average power like this. Here cos phi is 1. Power factor for a purely resistive circuit is 1. Phase difference is 0, of course. Phase difference between current and voltage is 0, but power factor is 1. So cos 0 is 1, Vrms into Irms. The same equation you will get it. What about in purely inductive and purely capacitive circuit? Average power dissipated is equal to V into I, that is average power dissipated Vm cos omega, sin omega t, voltage, current is Im sin omega t plus pi by 2. In the case of capacitor, in the case of inductor, Im sin omega t minus pi by 2. So what you will get? Average power dissipated is equal to Vm and Im into, this can be written as cos omega t. Okay, I think I have done this once. So sin omega t into cos omega t. Of course, in the case of inductor, this becomes sin omega t minus pi by 2, becomes minus cos omega t. Only minus sign will survive. But since final conclusion is 0, final answer is 0. Whether it is minus or plus doesn't matter. So what happens to this? Both are the functions of time. Average of this is 0. Total it is 0. Right? You can expand this even if you want, no problem. It will become 0. So average value of sin omega t cos omega t is 0. So average power dissipated, of course, how can you prove it here? Average power formula Vrms into Irms into cos phi, where cos phi is pi by 2, cos phi is pi by 2, cos phi is 0. So average power is 0. So current in an inductive and capacitive circuit is called wattless current. It doesn't produce any loss of heat or a loss of energy in the form of heat. No heat energy is produced. Okay. That is talking about ideal capacitor and ideal inductor, not practically, because if you want to construct an inductor coil, you should take a coil. Coil will definitely have some or other resistance. Even if the resistance is very less, there is. So it will dissipate heat since it has got a little bit of resistance. But theoretically speaking, they don't dissipate energy in the form of heat. This is one part. Of course, final formula is very, very important, not the intermediate derivations. Just to know how the derivation has gone, okay? Because for entrance exam, from some corner, how to solve it may be needed. The solution may be needed. Okay, that is one part. Secondly, we have another one called LC oscillations. What are LC oscillations? We'll finish one by one. And its derivation I am not going to do now. I will do it later. But I will just mention what are LC oscillations. Okay. LC oscillation means you take a charged capacitor which is completely charged, take it from the battery and connect it across an inductor coil like this. Say this is capacitor. Say these are the plates these are the positions where the plate has lost electrons and those electrons have gone to this other plate, so it is negatively charged. Now when a capacitor is charged and connected across a coil, inductor coil, there is a jugalbandi here, competition. What happens? All the electrons, so when you charge the capacitor, battery has done the work and sent the electrons from one plate to another. As soon as you switch it on, the positive of the battery had attracted electrons, negative had them put them in the other plate, so this has become positively charged. As it loses electrons, this gains electrons and becomes negatively charged. Now, can these electrons come back? No, battery will not allow them to come back. Battery has done the work in sending them like this. Now, battery has been removed and this is connected across a coil. Now these electrons have got a chance of going back, even though this opposes, because when the charges flow through an inductor coil, there is a variable magnetic field. If the magnetic field varies, then that change in flux induces a current which opposes the change, right? But still, electrons can flow. They got a path. As the electrons flow like this, there will be a current like this, right? Because current direction is taken opposite to the direction of electron flow. So electrons start flowing from this end to this end, and there is a current, so this will be positive and this will be negative. There will be an induced EMF across this. Now, if this gets induced EMF, this starts storing energy in the magnetic field. Now this starts losing energy. The energy of the capacitor as it discharges, what do you mean by discharging? Electrons flowing from one plate to another plate. As it loses those electrons, the energy stored in the capacitor goes on decreasing. Where is that energy now? It should be appearing in the form of, it should appear in the form of either heat, light, whatever it is. It appears in the form of energy stored in the inductor in the magnetic field here. So there is a change in current, because you know that as the capacitor charges, initially the current is more. As the time passes, current becomes lesser and lesser. So there is a variable current flowing in the circuit. That induces an EMF here. Initially there was a voltage here. You know that Q equal to CV, you know this one? CV Raman, right? Q equal to CV and V equal to Q by C. So here was Q by C voltage. Now that voltage decreases, that appears across the inductor completely. Once all the charges flow across this, there is a complete EMF here, because you know that as soon as an inductor is switched on, it gets maximum EMF first, then the current, right? So there is a EMF here. Once all the EMF is switched over here, this gets its energy completely. Once all the energy is transferred to the inductor, here is a highest voltage applied, right? Full EMF, no EMF here. This becomes zero because it has lost all the electrons and those electrons have gone to the inductor. It's a very interesting one now. Now, okay, capacitor has discharged because capacitor has got a chance of sending the electrons back. And that energy is transferred to the inductor now. Now the energy is in the form of magnetic field. Okay. Now you see the capacitor. Capacitor is as if it is connected across a battery of EMF E, isn't it? Because all the EMF is transferred to the inductor and there is a battery-like arrangement here. Capacitor feels that it can get charged because it's a battery. It is like a battery-like an arrangement. So an EMF is connected across the capacitor. Capacitor can charge now. Again, capacitor starts charging and electrons will leave this plate and they will come back. So this gets positively charged and this gets negatively charged. So now once all the electrons are transferred, because this acts like a battery, once the electrons are transferred from one plate to another, capacitor completely gets charged and again it gets a voltage of Q by C. Once the capacitor completely gets charged, what happens? Again, there is a chance for discharging because this inductor coil is always connected here. Electrons can move back. This is simply like a simple pendulum or a loaded spring, right? What happens in a loaded spring? If you just pull it down and leave it, what happens? Once full, the energy becomes potential. The spring gets expanded completely. Then it becomes kinetic by the time it reaches the equilibrium value. Again, negative potential. Again, kinetic, potential, kinetic, potential. So it keeps on changing from kinetic energy to potential energy. So it is an oscillator actually. A pendulum, a loaded spring, they are oscillators. Why they are called oscillators? The energy oscillates between one mechanical energy to another mechanical energy. Potential to kinetic, kinetic to potential, potential to kinetic. So, and it becomes positive and negative. Of course, in the reverse case, it may get charged like this. I have to put like this actually. Right, in the other direction. In the next case, when the capacitor charges, it may be like this. Again, when it gets charged and when it transfers the energy to the inductor, the energy may be transferred to the inductor later, and again when it gets charged, this may be positive and this may be negative. So it keeps on changing. And even in the inductor, once this is positive, this is negative. Next time this may be positive, this may be negative. Because even in this case of a pendulum, again full potential and kinetic, negative potential, kinetic like this. So it keeps on altering or oscillating between two energies. So that's why this is called oscillation. And if you connect an ammeter here, how will be the current? Once the electrons will be flowing like this, another time electrons will be flowing like this, and they will be discharging the capacitor, charging the capacitor, and inductor will be storing energy and storing EMF, or EMF will be developed like this. Next time this plus, this minus. So there is a continuous transfer of energy from one device, capacitor, in the form of electric field, to another device, inductor, in the form of magnetic field. It is like volleyball, right? Nobody wants ball. They want to put the ball to the other court wants to put the ball to this court. Nobody wants to receive it permanently. They want to transfer it to the other court, opposite court as well. So this is an oscillation. This is called tank circuit. We call it as tank circuit also, because energy is stored here, right? Okay, LC oscillations. Now the question arises, sir, if it is oscillating, if the energy is oscillating from one component to another component, and if it is transferred from one component to another component, how many times it is transferred from magnetic field to electric field to magnetic field? That is what you call frequency, right? If you're in a loaded spring, if you just pull it and leave it, how many times the kinetic energy is transferred into potential to kinetic to potential, kinetic, potential. That is called the number of oscillations made in 1 second, frequency. What is the frequency of this LC oscillator? Frequency omega naught is simply the same equation, because you know that even in series resonance circuit, the frequency at which the current becomes maximum is not decided by resistor. Frequency is decided by L and C. And if you change the resistance of a series resonance circuit, resonant frequency doesn't change, because resonant frequency is decided by L and C, not by R. R decides how much current should flow in the resonance condition. What is the maximum current that has to be that is flowing in the circuit at the time of resonance? That is decided by resistor, because Im maximum is equal to Vm by R. The peak value of the highest value of peak current is Vm by R. Okay, omega naught is 1 by root LC. This is the resonant frequency, or nu naught is equal to 1 by 2 pi root LC, right? Right. This is how the oscillations are made. Of course, how did you get this equation, sir? We will derive it later, because this derivation is not so important for the examination point of view. I'll do that in the next class, because I want to say the theory part of it first. Okay. So now suppose you are asked to write what is the equation for the energy stored. Now when the current is flowing in the circuit, Im be the maximum current flowing in the circuit. When the capacitor stores energy, let Qm be the maximum charge stored in the capacitor. So energy stored is equal to either half Li square. What is half Li square? Half Li square is the energy stored in an inductor. We have derived this. Please go back and see one of the video. We have derived the equation for the energy stored in an inductor. Half Li square, half Lim square. It is same as Qm square by 2C, right? You know, energy stored in a capacitor is half CV squared Q square by 2C formula. But if you want to know full energy, see, what is the full energy of a loaded spring? Half Kx squared or half Me squared. X is the displacement. What is the full energy of a pendulum? Either mgh or half Me squared. Same. Maximum velocity square or full height mgh. Similarly, what is the full energy stored in the capacitor? Half Lim square, when no energy is stored in inductor. What is the full energy stored in the capacitor? Qm square by 2C. Full energy stored in the capacitor is Qm square by 2C when there is no energy stored in the inductor. This is the full energy stored in the inductor when there is no energy in the capacitor. So these are the two energies, maximum energies. Suppose at intermediate case, if I is the current, I is the current, at some case it is not maximum. What will be the energy stored in the inductor? Not complete. Some energy is transferred to the inductor and remaining energy will be in the capacitor. Now what is the charge in the capacitor? Q, say. Now how do you write the same equation? U as. Now what is the energy stored in the inductor plus energy stored in the capacitor? Right? Hope you have followed this equation. Y plus here, Y equal to here, isn't it? See, when the pendulum is here, full kinetic. When the pendulum is here, full potential, because it stops. Potential, full kinetic, potential, full kinetic, full potential. In between, what is the condition? Some potential and some kinetic. Now when it is in between somewhere here, its velocity is not maximum, it is some other value, V. Potential is, energy is not maximum, it is some value in between. It's a sum, the sum of kinetic and potential energies at an intermediate position must be equal to the full potential here, full kinetic here. So I can write this equal to, right, same. It is the full energy stored in the inductor in the form of magnetic field, full energy stored in the capacitor in the form of electric field. When the energy in the form of electric field is in the capacitor full, there is no energy in the magnetic field. So I can't write plus. Or either this one or this one. That is equal to some intermediate energy in the inductor plus the energy in the capacitor. Because Q is not the maximum charge, it is some charge in the capacitor when the current through the inductor is I. It is not M, it is not M maximum alloy. That is not the maximum value. Half Li square plus Q square by 2C. So half Li square plus Q square by 2C or Qm square by 2C, half Lm square. So we will do that later, okay, the derivation part. Okay, that is one thing. And one more thing is transformer. We will study the transformer also. What is a transformer? Okay, right. Transformer is a device which works on the principle of mutual induction. This is a very good question to be that may be answered in the final exam. Where you write some few points and transformer. What is a transformer? Transformer is a device used to increase or decrease the AC, amplitude of AC. It doesn't change the frequency, number of oscillations are not changed. So transformer is a device used to increase or decrease the value of AC. And it works on the principle of mutual induction. If it works on the principle of mutual induction, it must have two coils. Am I right? So it has two coils. One is primary and another is secondary, like this. So this is primary and this is secondary. Okay, I'll call it here. And both the coils are wound on a iron rod, iron block, so as to increase the magnetic flux. Okay, so that is symbolically shown like this. Actual diagram may be like this. So here is a iron block like this, say, and it is made into slices like this. Of course, I will say why it is made into slices. And it is hollow here, and it will appear like this somewhat. And here is the coil wound over it. This is primary is wound over, so this is one and another one. And here is the secondary, and here are the turns. So this is primary and this is secondary. This is a core, iron core. Now, so AC is input AC, right? This AC input. And AC output, again output is also AC. Remember, we have used, if you will use this transformer in a, when we explain a device called rectifier. Rectifier is a circuit which converts AC to DC. But we show a transformer in a part at a corner, but transformer is not the part of rectifier. Rectifier is a diode. Diode acts like a rectifier. But if you want to increase the AC or decrease the AC first, if you want to do that first, you need a transformer. But it is not rectifying. Rectifying is done by diode. Okay. So AC input, AC output. This AC may be of high peak value, say 100 volt. This may be of a low peak value, say 10 volt, or maybe ulta. This may be 10 volt and this may be 100 volt, maybe anything. That depends on the number of turns. Now, how does it work? How can you increase the value of AC or decrease the value of AC, sir? Here we are mainly considering about the voltage peak value, amplitude peak value of voltage. Suppose a transformer gives high value of amplitude volt or voltage amplitude. Say this is the peak value of say 10 volt, and or RMS also you can write. Say this is say of some 2 volt. 5 times it is decreased, right? 10 volt AC, peak value AC is decreased to 2 volt peak value AC. But number of cycles same. Remember, transformer doesn't change the frequency. How many number of cycles are repeated this per second? Say 50 hertz, 50 cycles. This is also 50 hertz. No change in the frequency. Input and output frequency of a transformer is same. Only the input and output, if you draw input and output in the same graph, it will be like this. Suppose this is 10 volt and minus 10 volt, same cycles, 2 volt output. This is the output. So this is 2 volt, this is minus 2 volt. That's how it does. Number of cycles are not changed. So number of cycles remain the same. I can use chalk, color chalk I have today. So this is the output, like this. Now, so how does it work, sir? How is it possible to decrease the voltage or increase the voltage sometimes? Depending on whether voltage is increased or decreased, we have two types of transformer called step-up transformer and step-down transformer. Step up and step down. What do you mean by step-up transformer? If the voltage at the secondary, I write it as Vs, voltage at the primary are such that if voltage at the secondary is greater than the voltage at the primary, then it is called step-up transformer, and if voltage at the secondary is less than voltage at the primary, then it is step-down transformer. This is a step-down transformer now, what I have written here. 10 volt peak to peak, and it has been decreased to 2 volt. Now, whatever Vs and Vp I have written, say they are RMS values. I need not mention only peak values, right? RMS value. If RMS value of input is more, RMS value of output is less, definitely it is a step-down transformer. You just stick on to one set of values, either input RMS, output RMS, or input peak, output peak, anything. Okay. So if the output voltage at the secondary is less and voltage at the primary is more, then it is a step-down transformer. And if the voltage at the secondary is more and voltage at the primary is less, then it is a step-up transformer. How do you achieve this? Very simple, depending on the number of turns in the primary and number of turns in the secondary. Suppose you want a step-up transformer, have more windings, more number of turns in the secondary and less number of turns in the primary. And if you want to have a step-down transformer, less number of turns in the secondary, more number of turns in the primary. This is a step down, what I have shown, because for our external just appearance itself, this feels that we have less number of turns here. So step down. If the number of turns in the secondary are less, number of turns in the primary are more, step down. Number of turns in the secondary are more and number of turns in the primary are less, then step up. So Ns, if it is greater than Np, secondary less, step on. Yeah, Vs, yeah, it is step up. Secondary are more, number of turns in the secondary more, number of turns in the primary more, yes, primary less. If the number of turns in the secondary less, number of turns in the primary more, step down transformer. Sir, all these step up, step down are named according to the voltage, not according to the current. It is not according to the current. We name it according to the voltage, whether voltage is decreased or voltage is increased. If the AC voltage peak value decreases at the output, step down. If the AC peak value increases at the output, step up. Okay. Sir, why don't you take current? Current becomes ulta, because whatever it is, voltage increases or decreases, energy should not be lost, right? Because it cannot be. Energy is always conserved. Here, electrical energy. Sir, what about input electrical energy and output electrical energy? Suppose IP is the primary current and IS is the secondary current, because some current should flow. Sir, how does current flow? It's a mutual. I already have given the clue. It's a mutual induction process. What is mutual induction? You know the Faraday's experiment, coil and coil experiment. Magnetic field of one coil is changed. It induces an EMF in the secondary coil. Same thing happens here. When you pass AC through the primary coil, what type of current is flowing through the primary coil? It is a variable current. When variable current flows through the primary coil, the magnetic field produced by the primary coil keeps on changing, and that magnetic field is linked to the secondary, since both are wound to the same core. They are very close, and that change in EMF is linked to the secondary. And that change in change in magnetic flux linked to the secondary. Change in the magnetic flux linked to the secondary induces an EMF in it and induces a current. That is mutual induction. Change in the magnetic field of one coil induces an EMF in the secondary coil. That is mutual induction. So that happens here. So we get an EMF here. Now, if you try to write the formulas for the induced EMF, Suppose induced EMF in the secondary, of course I can write it as Vs because I have taken it as Vs, is minus Ns, number of turns in the secondary, d phi by dt. We have derived that mutual, self-inductance formula and all, right? One coil kept inside the other, you have to remind it now. So induced EMF in the secondary is, because this is simply Faraday's law, induced EMF is equal to minus d phi by dt. Of course it depends on the number of turns also. If you have more number of turns, more flux is used, and if you have less number of turns, less flux is used. So what is the induced EMF in the primary? Suppose you write, suppose you do the reverse case. You see, even step-down transformer can be used as step-up. How? Just recall that derivation of mutual inductance. When one coil is kept inside another coil, the mutual inductance formula got the same. Whether it is the change in the magnetic field produced by the primary coil linking the secondary, or whether the magnetic field produced by the secondary coil linking the primary, whatever it is, self-inductance formula is same. L is equal to mu naught N1 N2 pi R1 square. The smallest coil area is the one which uses a flux. Okay, in such a case, so suppose you give the input here and get the output here, you can interchange it. Now suppose input is given here and output got here, it is step-down transformer. Give the input here, let the magnetic field of this coil will change, let it produce an EMF here, more number of turns here, step-up transformer. So what is the EMF induced in the primary? If alternating voltage is applied at the secondary, it is equal to, so I will write it as Vp minus Np into d phi by dt. A very simple equation. Number of turns in the primary into d phi by dt. Now you get the ratio. What you will get? Vs by Vp. I don't use these notations. Hope you have got this idea, right? This is simply Faraday's law. But number of turns you have to make it. So one thing you have to remember is you can use the transformer with the in the reverse way also. You can give the input here, get the output here, or give the input here, get the output here. It is mutual induction. Mutual induction between a pair of coils doesn't depend whether you give the input to the smaller coil or larger coil. Vs equal to Vp. So that is equal to, everything will cancel. Minus also will cancel. Ns by Np. Right? See, same thing we have arrived. So in a step-up transformer, Ns is greater than Np. In a step-down transformer, Vs is greater than Vp. Okay. Then, what else? Right. Current. That is what we were talking about. Current. In the case of transformer, input energy and output energy must be same. Let I be the current. That's where we have got a diversion. How did you get current? The change in the magnetic flux produced by a coil, when it is linked to another coil, in order to oppose it, it induces a current. The current flows in such a way as to oppose the cause, oppose the change in the magnetic flux. So you should get a alternating current primary in the primary coil, alternating current in the secondary coil. Now what is the power at the input? Power input must be equal to power output, isn't it? It should be equal, because if you suppose it is an ideal transformer, a transformer is ideal, no resistance to the coils, no loss of energy in the form of heat. It is not lost in the form of any other energy. Every electrical energy in the input is got as exactly electrical energy at the output. Then power input must be power output, then it is called ideal transformer. We will see what is the problem practically. Pi equal to P naught, then V input means primary, Vp into Ip must be equal to Vs into Is. Correct? If Vp into Ip is equal to Is into Is, now Vs by Vp, bring this here, must be equal to Ip by Is. So Vs by Vp must be equal to Ip by Is. This is the only one which is changing its this appearance, you see. Secondary, but this one primary. Then what do you mean by step-up transformer? In a step-up transformer, voltage increases but current decreases, because total energy must be same. You can't have both the increase. You more energy got. You can't create energy from somewhere else, right? You can't create energy by nothing. There should be a transfer of energy from one form to another. So when in a step-up transformer, voltage is increased but current is decreased. In a step-down transformer, voltage is decreased, current is increased, so that product of voltage and current is always same. That is nothing but power is same. Rate of energy lost per second. Okay. So this is the important formula that is needed here, right? So in a step-up transformer, voltage is increased, current is decreased. But you need not talk about current at all. In a step-down transformer, voltage is decreased, current is increased. But we name step-up or step-down depending on the voltage, not according to the current. So this ratio is very, very important. Vs by Vp is equal to Ns by Np is equal to Ip by Is. So Ip by Is, that ratio is different. Just from this equation we have got it. Now, usually in practical transformers it is not the same. Pi is not equal to P naught and its efficiency is not 100%. If output energy and input energy are same, then the efficiency is 100% for ideal transformers. For practical transformers there are so many problems. What are the problems associated with practical transformers? Output energy is not equal to input energy. In the sense, I am not saying total energy. Total energy at the input and total energy at the output must be same. But we don't get full energy at the output in the form of electrical energy. That is the problem. So output energy will not be in the electrical form. It may be in the heat form. So in a practical transformers, energy is lost in the form of heat due to following reasons. This is a very important question here. What are the sources for the energy loss in a transformer? 1. Resistance loss. Okay. What do you mean by resistance loss? In order to have a better flux linked, we have more and more number of turns in a transformer. When you have more number of turns, obviously the wire will be of high length. When the length of a wire is more, resistance will be more. And when the resistance is more, you know that I squared R loss, power is equal to I squared R. So in a resistor, there is a loss of power, and resistor always consumes energy in the form of heat. So there is a loss of energy in the form of heat due to resistance of the wires. So the wires used for primary and secondary coil are very long. They will have some resistance, so they will produce some heat energy when current flows to them. How to avoid this? Use the best coil having a thick dimension. That means its area of cross section should be more. You know that resistance of a wire is rho L by A, and use a best wire, say copper. If you use silver, it's well and good, but if you have a silver wire wound transformer, I think you need to have 2 guards for that, because somebody will steal it, and it is costly. So, and the length, however, you can't avoid it, because you have to use the more number of turns, increase the area. Best copper wires with larger area of cross section, make the resistance as less as possible, so that you can reduce the heat energy loss due to resistance. Of course, loss is heat energy loss due to resistance. 2. Name is resistance loss, right? Heat energy loss due to resistance. Okay. Due to resistance, I'll write heat energy due to resistance. Second one, flux leakage loss. Flux leakage loss. Loss due to flux leakage. Okay. Instead of like loss due to flux leakage. What do you mean by loss due to flux leakage? All the magnetic field change produced in the primary may not be linked to the secondary. Suppose you use without using the iron core, simply wind 2 coils and keep it closed like this. What happens? The magnetic field of all the primary may not be linked to the secondary. These magnetic fields are lost. So usually when you need to use a magnetic field and coil, what do? You keep an iron core, right? What does the iron core do? It simply intensifies the magnetic field. All the magnetic field lines which are spread are concentrated by a ferromagnetic material. Best is iron. So that is why we used an iron core. Magnetic field of the primary may not be linked to the secondary directly or completely. In order to reduce it, we use an iron core, and iron core intensifies the magnetic field and increases the flux. So that's how we can decrease the flux leakage loss. But as soon as you use an iron core, there are some other problems. 1. Loss due to eddy current. Remember now? During the time when I was discussing about eddy current, I mentioned this transformer. Eddy current loss. Whenever a magnetic mass, when a mass of magnetic material is kept in a variable magnetic field, some small loops of currents are produced inside the core. Suppose you move a plate, metal plate inside a magnet field and take it outside, and again inside the magnetic field and take it outside. Continuously if you do so, you find that small loops of currents are produced inside the core, and those loops of current are called eddy currents, and they produce heat energy, that is a loss. So how to reduce the eddy current in this core? Slice it into pieces as you slice the bread into different pieces, and as you put jam inside the bread between the two pieces, similarly you put gum between these two slices. So you will have separate plates like this, right? Cut it into plates like this, like this, like this, and paste them using a gum again. So you have the same amount of mass of solid now, that is iron. You have the core, but that core is not made up of a single material. It is different plates, and they are gummed together using an insulating gum. Now eddy current cannot flow from one plate to another plate, since it is insulated from insulated using a material, right? So we use a single word to explain it. How to reduce eddy current loss? By using laminated core. What is laminated core? The whole core piece is cut into slices and pasted using an insulating gum, so that eddy current doesn't flow everywhere. So eddy current loss can be minimized by using a laminating core. Then fourth one. So energy loss due to resistance, energy loss due to flux leakage, energy loss due to eddy current, and energy loss due to another magnetostriction loss. What do you mean by magnetostriction loss? You know that usually in a transformer, what happens is when you pass AC, this core gets magnetized. When a material is magnetized, there is a decrease in its length, that is called magnetostriction. When you demagnetize it, it comes back to the original value. You are passing AC here, so AC increases, decreases, becomes zero, increases to the negative peak and decreases. 2 times it gets magnetized and demagnetized in every cycle. 100 times it gets magnetized and demagnetized in 1 second, because what the frequency we are using in our home appliance is KPTCL AC. That KPTCL AC runs at 50 Hertz. 50 cycles are repeated in 1 second. In each cycle it gets magnetized twice. 100 times it gets magnetized and demagnetized. 100 times its volume or dimension collapses, comes back to the original value, collapses like this. It vibrates. When it vibrates, it produces a sound at 100 Hertz, which is audible. You get a sound. That is a loss of energy. So you don't get output as a complete electrical energy. Magnetostriction loss, and of course you can use best material which shows very less amount of magnetostriction. Another important loss that occurs in a transformer in the form of heat energy loss is loss due to hysteresis. Do you remember what you have studied in hysteresis? When you study magnetic materials, you come across this, right? Hysteresis loss, energy loss due to hysteresis. What do you mean by energy loss due to hysteresis? We have completely studied it. When a ferromagnetic material is taken through a cycle of magnetization, magnetizing, demagnetizing, magnetizing in the reverse direction, again demagnetizing, there is a loss of energy inside it in the form of heat. So that produces heat energy. So heat energy may be produced due to all these 4 cases, and also due to hysteresis. So how can you minimize the hysteresis loss? By using a ferromagnetic material as the core, which has got low hysteresis loss curve. You do remember that curve? It is magnetic intensity versus magnetic induction, and the curve will be like this, and starting from here and coming like this. This area of the hysteresis loop must be very less, so that heat energy loss is very less. So this is another loss. Usually in the examination you will be asked to mention the energy loss in a transformer. Mention the sources or mention the reasons for the energy loss in a transformer. Especially all finally lead to the energy loss in the form of heat. right? So what are the sources for the, what are the reasons for the energy loss in a transformer? Why the output power is not exactly equal to input electrical power? Output electrical power is not equal to input electrical power. It is not ideal transformer. Why? In practical transformers, you have to mention it, energy loss in the form of heat can occur due to resistance of the wires. Heating effect can occur. That is called Joule heating, right? Because of the resistance and collision of electrons, the heat energy is produced. That is called Joule heating effect. So the resistance of the wires, since we are using very long wires for windings, that may lead to the heat energy loss. And how can you minimize it? You can minimize it using best copper wires of more cross-sectional area, and the copper wires have less resistance. And flux leakage loss. The magnetic field produced by the primary, and when it varies, the total magnetic flux may not be linked completely to the secondary, and that is called flux leakage loss. The magnetic flux of the primary may not be linked completely to the secondary. In order to minimize it, we use a ferromagnetic core as the base for the windings, and which will intensify the magnetic flux, and it will concentrate all the magnetic field lines or magnetic flux, and makes the situation such that most of the magnetic flux is available for the secondary. So using a core, you can decrease the flux leakage loss, right? You can make maximum amount of flux linked to the secondary. Eddy current loss. So when a magnetic material is kept in a varying magnetic field region, or when a magnet is taken in and out of the magnetic field region, small loops of currents are produced inside that core, and that is called eddy current. When eddy current is more, it also produces heat energy loss. And you can use a best material, you can use a laminated core. What is laminated core? Making it into slices and gumming it again using a laminated insulating gum, and that avoids the flow of eddy currents, and of course still there will be some loss of it. So you can use a single word here, laminated core. Eddy current loss can be minimized using laminated core. And the magnetostriction loss, of course, it is not a very important one. You can directly jump into this one. Hysteresis loss. So when a magnetic material is taken through a cycle of magnetization, there will be heat energy loss produced inside, and that can be minimized by using best material, right? Like which have less hysteresis loss. So you may be asked to mention it, that's all. Energy loss due to resistance of wires, energy loss due to eddy current, energy loss due to flux leakage, energy loss due to hysteresis. So these three, except fourth one. Of course, fourth one better you remember it. Yeah. Now, so this is a very important question for the final exam. Transformers. Sometimes they will ask for 3 marks, 5 marks, something like that. So explain a transformer. On which principle does it work? What is a transformer? What does it contain? How does it work? Transformer is a device which converts AC to, transformer is a device which increases or decreases the voltage, and in the examination you will have for the examination, this is a very important question. You may get 3 marks question or maybe even 5 marks question to explain a transformer. You have to start from the principle and working, right? Transformer is a device which increases or decreases AC, alternating current, its amplitude, and it doesn't change the frequency. It works on the principle of mutual induction, and it contains a primary coil and a secondary coil wound on a ferromagnetic core, and because of the change in the magnetic flux produced in the one coil, there is an induced EMF in the secondary. And what is a step-up transformer? What is a step-down transformer? This equation is very important. All these things, of course, it arises from this, and very simple explanation. So a very important question. So we have covered 3 parts here today. One is power in an AC circuit, and power in different components, a formula for power. Of course, even though the derivation of formula for power is not important, but its formula is important. And then LC tank circuit, that is oscillations, its frequency, and the equation for the energy stored, and then this transformer. So we will meet in the next class with some more derivations. Thanks for watching this class. Hope you will study well. Take care of your health. We will meet in the next class with another derivation. Thank you.